Okay, so this is where we left off. We talked about a couple of traversals through the tree. And the reason we talked about a few different traversals is because it's a nonlinear data structure and there's perhaps a less obvious way to traverse these elements. A linear, it's more obvious. Nonlinear, well, we have decisions to make. And then we also talked a little bit about the computational complexity of these analysis, of these traversals. And at the end of the day, there are n nodes you got to look at. You put your finger on each node, it's going to take n steps, right? But I did make a point to emphasize the difference between the number of nodes when the question is about what's the computational complexity relative to the number of nodes versus what's the computational complexity relative to the height of the tree. Because there's the relationship between the number of nodes in a binary tree and the height of a tree. And that relationship is exponential. It's going to be on the order of, the number of nodes is going to be on the order of, do I have it here listed? Yeah, I guess I don't have it listed here, but 2 to the power of h, it's going to be on the order of that. When I say order of, I mean close enough. We don't need to get more precise than that. So that's where we left off. But now, okay, so we talked about a binary tree and we talked about a couple of traversals, but a binary tree at the end of the day, it's a tree, and the rule is each node can have no more than 2 children. So how do we make a binary tree? Well, before we make the binary tree, we need to define what we want it to do. And we're going to do that with an interface. So let's make a binary tree interface. What do we want to do? Check if a given element exists in the tree, sure. And to be clear, we can add more or take some of these things away, whatever. It's just kind of, it's not arbitrary, but you know, we've got the freedom and flexibility to do whatever we want here. So what do I want to do? I'll check if an element's in the tree, check the number of occurrences of a given element, right? If I have a tree, like how many 7s are in this tree, right? Check if it's empty, get the size, various traversals through the tree, because why not? We want to be able to add an element too, and remove elements. But, you know, add element, where should it go? And this is reminiscent of the bag, right? When you add an element to the bag, where should it go? Well, it depends. Was that an indexed bag or a sorted bag? If it's a sorted bag, it's got very strict rules. Indexed bag, well, you just specify the index. We're going to have a similar thing here. And remove elements. Which one? From where? So, you know, we have to get a little bit more specific here. So it's removing something to a stack was more straightforward. It's very well defined, but like the bag and the binary tree, it's going to depend on the type of binary tree. And the one that we're going to implement, not right now, very shortly, is going to be a binary search tree. It's not it's a binary tree, but it's a very specific type of binary tree, binary search tree, that has some really interesting properties. But here is our general interface for a binary tree. It's going to be iterable because we'll define an iterator for it and we want to be able to iterate over it. And we've got, okay, add, remove, contains, count, is empty, size, an iterator. And then we actually have a variety of different iterators that we can create. So this particular class is going to be iterable, and it's actually going to have 1, 2, 3, 4, 5 different methods that return an iterator. Now, mind you, the regular iterator is just going to return one of the other ones. But we could iterate over this collection in a variety of different ways, so let's just have it return whatever iterator we want. Do you want to do a pre-order traversal? Do the pre-order iterator. In order? Call the in order. Just whatever. That's basically it. It's going to be generic, right? Binary tree of arbitrary elements, but that's the idea. That's what we want. Any questions about what you see? If you go and you look at the actual interface I have on the course website, like if you download it, you'll see a lot more details here. Here I don't include the Java doc comments, right? But they are there. They explain each of these methods. So how are we going to implement it? Well, no binary tree implementation is being created. It's going to inherit from a specific binary tree implementation. So We're not going to actually implement a binary tree. We're going to implement a binary search tree. That's going to be like the next topic. And one way to implement a binary tree, binary search tree, but to build it is with like a link structure. We could do it with an array. We could do it with whatever container we want, really. But a link structure is relatively natural. It's the same idea as like our linear link structures, except instead of each node having data and a next, each node's going to have data and a left and a right. That's what we're going to do. So we're going to need a new node class. But the node class is going to be used to actually, like, it's going to be a series of nodes that actually makes up the binary tree. So we'll have a series of nodes. We'll also have some field to keep track of the size. And use a field, and we'll have like, yeah, field reference the root node. Because if we have access to the root, we can access everything in the tree. Cool? So far, so good? So let's say, okay, binary tree node. Here's the idea. You've got some data. Really, data is going to be a reference variable. So really, there should be another arrow in that image, but whatever. Some reference variable to some data that we're going to have of some type t. And a left and a right, where left and right are going to be reference variables to binary tree nodes of type t. Yeah. So we can make a new standalone class, or we could do another like internal class. Remember how we made like the node class, but we also made it an internal class where it was a class written inside of another class? Remember that? Well, we did do that, and if you don't believe me, you can go check. But here's what we're going to have right here. So here's an example of what my node class looks like, but it's a private static one, meaning this is an internal one. I could make it public, but of course if I did, I'd have a bit of an issue because if I had like a, sorry, not public, but like a standalone class. If I made it a standalone class, and I already have a standalone node class, I'd have a bit of an issue calling this one node as well because there would be a name conflict. So I'd have to call it like binary node or something. But this is my example of the internal one, so it's private static. It's got 3 fields, data, and a left and a right node. They're the left and right children. It's got a constructor. It's got 2 constructors. Get data, get left, get right, set right. So this is mutable, and if I were to write unit tests for this, I'd have to be very careful, but it is, there we go, that's it. It's a relatively straightforward class. It's very stateful, but, you know, data structures. It is what it is. Any questions about this? It's basically the same as the regular, like the old node class we looked at, except it's got an extra field, and a getter and a setter, an accessor and a mutator for that new field. New being, well, instead of next, we have a left and a right. Cool? Yeah, happy, sad? Questions, concerns? All right, well with this, we could start to actually implement a binary tree. Now again, we're not actually going to implement a binary tree, we're going to implement a binary search tree, which is a binary tree, but a specialized version. But even though we're not going to implement this general binary tree, we could start to think about what could these methods look like in a general tree situation. A general binary tree situation, pardon me. So what could they look like? Well, here's an example. Here's a size method. Now, take a moment and look at this code, and I'll keep my mouth shut for a minute. I'll let you look at this code and try to make sense of it. So first thing if we were making an implementation of a binary tree, and we had the field size that just kept track of the size, this would be entirely unnecessary. You just return the value of the field size. But let's say you have some binary tree and you want to know how big is it. Well, easy, count the number of nodes. It's what you would do. So how many are there? Well, how do we do that? Well, to me, the easiest way to do it is just, well, use a recursive function that goes like this. Given some node, if that node doesn't exist, how many nodes are there? 0. Otherwise, it exists, meaning it's 1 plus the size of my left subtree plus the size of my right subtree. And how do I get the size of the left and right subtree? Recursively. I've got a method that does that. It's the size. Just call it again on that node. If it exists, count it. If it doesn't, return 0. If it exists, count it. If not, return 0, and so on. What else do you notice about this one? There's an obvious observation one could make. Perhaps it's so obvious that it feels like a trick question. And some people asked about this in lab before. There was somebody that said something, but I didn't hear what you said. Okay, maybe it's too stupid of a question that you're confused. There's 2 size methods here, right? But one's private and one's public. But the one that actually does anything is private. The public one just delegates the work to the private one. So what's going on? Well, when I want to know the size of the whole tree, what node must I give it? The root. So if someone is interfacing, if someone is using this class for a binary tree, and they want to know the size of it, they must call it on the root node. So just make a public function that just automatically calls this recursive function on the root node. So the public one isn't recursive, but it does the initial call to the first recursive part of it. And this came up in lab. Some people were a little thrown off. Maybe thrown off isn't the right word, but a number of students made a key observation in the lab about like, well, they were writing the linear search method. And when writing the linear search method, they were getting really hung up on the fact that like, well, someone could call this function. When doing the linear search, you would typically start it at index 0. Start at the beginning. But students were making a point to say, but there's nothing stopping someone from just arbitrarily calling it the first time at index like 5. Thereby skipping 0 through 4, which is a problem. And you're absolutely correct. That's absolutely true. Because if you want to do this, you want to start at the beginning. So often what you do is you make like a public helper method that does the initial call to start the recursive where it should start. This is a common pattern you see. It's not required, but it's not atypical by any means. So that's the idea behind what's going on here. There's the public one, it takes no arguments. There's no parameter. But it just immediately calls the recursive one that needs to take a node. Well, which node? The starting one, the root. Yeah? Happy? Sad? If this isn't obvious to you, we'll see a few more examples and maybe it'll help. But really, what it's trying to get at is eliminate the need. If we didn't have this public one, and someone wanted to use, get the size, they would need to call it on the tree's root. Well, why force them to throw in the root as an argument when it could just do it automatically, right? That's what that's doing. Any questions about this? Okay, yeah, so what's the computational complexity? Where there's n nodes, it's n. You count them all. Now, how many things, though, will this actually put, will it actually, like, how many times will this function actually be called? More than n. Because if the number of nodes is n, imagine I'm a leaf node, okay, that I need to get counted. But this does make a call to my left and right. So I'm going to go to my right, but I'm a leaf node, so I don't really have a right. But I do call this recursive function, recursive method, on my left subtree and my right subtree, meaning I make call frames for that. They just immediately return 0. So it does actually do like extra work, but it's still big O of n. We could change this out a little bit by saying like, okay, if your left exists, call it, but that actually ends up kind of messing up the pattern here anyways. And I'd want to be able to call it on an empty tree in the first place. Like I should be able to call it on a tree that has no nodes and have this return 0. So it is designed this way for a reason. And if you can't quite see it yet, I suggest working out a couple examples by hand and it'll click pretty quickly. So taking this idea, have a look at this code. What is this code doing? I'll give you a moment. Take your time with it. I don't want to rush you. Do you have a question, or are you just wait? Give everyone a chance. But do you have a question? You just want to answer? Okay, we'll come back to you in a moment. To get it out of the way, this clearly follows the same pattern as the last one, with a private recursive one and a public one that just kind of starts it. So what were you going to say?
I was going to say it's doing a recursive linear search to see if the needle is contained within.
So it's doing a recursive search. Now, I wouldn't call it a linear search, but it's doing a recursive search. And how is it doing it? Well, what does the code say? Recursive algorithms tend to be fairly, I got to be careful how I word this. I want to say simple to explain, but non-trivial to understand. I don't know if that even makes sense, but let's go with it. So if the current node doesn't exist, is it the thing I'm looking for? No, that's easy. If the current node contains the thing that I'm looking for, does the tree contain the thing I'm looking for? Yeah, great. So if the node's not null, so I'm some general arbitrary tree with some arbitrary number of children to the right and to the left, or left and right. I exist. I'm the root node of this tree, but I don't contain the data I'm looking for. Can I conclude that that thing is there or not yet? No. I can only conclude that once I've looked at everything over here and everything over here. So the idea is, if I exist, if I don't exist, it's not in this node. Or neither of my children, because if I don't exist, they don't exist. If I exist and I contain the data I'm looking for, I'm done. If I exist and I don't contain the data, perform a search over here and over here. If it's in here or here, return true. If it's not in here or here, we return the result of, well, it would be false, right? Because we're only ever, first of all, this is a short-circuited OR too. Meaning, first we look at the left subtree. Actually, for some reason I think in Java it goes right to left. I could have it backwards. It doesn't really matter in terms of order. But now I'm actually curious. Pardon?
Or just kind of unions it anyway.
Yeah, but let me clarify what I was saying. And I'm not actually 100% sure on this because every language is a little different. This line of code here makes two calls to functions, right? But a computer can only run one thing at a time, meaning one of those two has to run first. And which one runs first? This one? This one. And I can't remember which order Java does it in. It doesn't really matter, but it's interesting regardless. But let's ignore that. Short-circuited. Let's assume we search over here first. If calling this ultimately gives me back a true, I don't need to return, I don't even need to look over here anymore. So we actually only end up looking over here, which is pretty great. But if it returns false, well, we still have to look over here. I think for the sake of really wrapping our heads around this algorithm, let's do a really quick little example. Can you see over here reasonably well? Cool. 7, 4, 9, 10, 1, 1. Let's say this is our tree. And let's say, we'll do two examples. One where we're looking for a thing that does in fact exist. And another one where we're looking for something that doesn't exist, just to see how it works in both cases. So let's say we're looking for the number 10. All right? So I start here. Does it exist? Yes. Okay. Is 7 equal to 10? No. So we need to call on the left subtree. Does it exist? Yeah. Does 4 equal to 10? No. Call it again on this subtree. Does it exist? Yeah. Does it equal? No. Call it again on this subtree. Does it exist? No. Return false. Yeah? We return false. So this has one false. We still need to look at its right subtree though. Because this could return true. And false or true gives me back a true. So we need to look. Doesn't exist, it's false. Okay, so we get back a false. That means we get a false here. Right? False or false? False. So, okay. Let's look at the right subtree. Does it exist? Yes. Is 10 equal to 10? Yes. Return true. False or true? True or I don't give a shit. It's true. We found it. But let's say we were looking for 11. Let's carry on as if we were looking for 11 from there. All right? So no, 11 isn't 10. Look over here. No, we get a false because it doesn't exist. Look over here. It doesn't exist. We get a false. This returns a false here. False or false is false. False or false is false. We must look to the right subtree. Does it exist? Yes. Is 11 equal to 1? No. Go to the left. Does it exist? Yes. Is 11 equal to 1? No. Go to the left. False. Go to the right. Doesn't exist. False. False or false. We get a false. We go to the right. Doesn't exist. Return a false. False, false, false. False or false. Returns false. Doesn't exist. It's not there. 11 is not in this tree. When in doubt, what does the code say? Follow the algorithm. Draw it out. It'll help. Pretty neat though, right? Now what's the computational complexity of this? Take a moment and think about it. If there's n nodes, and I'm looking for something, and this is the pattern, what's the worst case scenario? You look at them all. If I have n nodes, that means I need to look at all n nodes. Now, we might get lucky in that it's the root node. And we might get lucky that, maybe it's not the root node, but it's in the left subtree, meaning we don't even need to look at the right subtree. That's true. That's a good thing. But in the same way that we might get lucky in a linear search where it's near the beginning versus near the end. It's still going to be linear relative to the input size, where the input size is the number of nodes. Any questions about this contains here? And now traversal. What would the traversals that we looked at look like? Well, this one's basically it. Now notice this is not the iterator methods. These are just, let's say we were doing a traversal to just print out the values. So here is a pre-order. You print out the data, then call pre-order on the left and pre-order on the right. What would the in-order look like? This is an exam question. You bet your ass this question is going to be on the exam. What would the in-order look like?
Pre-order left, printed out, and pre-order right.
Entirely incorrect. You want to try again? You just don't even realize what you said, I'm guessing. Does anyone know what he said wrong? You want to do an in-order traversal, and you start by calling a pre-order on the left? There we go. You want to do an in-order on the left, print it out, and then do an in-order on the right. Yeah, there you go. Did no one notice what he said wrong, for real? You were reading this, yeah. Here's an example of, for the sake of just showing you something different, before I just printed out the contents. Here, I'm not actually printing out the contents. What I'm doing is I'm saving the contents to a bag, an array index bag in that order. If you're saying, why? Does this have any meaning? Literally just to show you that it doesn't really matter what I'm doing with the data. It's just when I'm doing whatever it is the hell I'm doing to the data is what is important. It's the when relative to the other recursive calls that's important. Any questions, thoughts, concerns, observations, points? Nothing. Everyone's happy. Everyone's very happy. Nothing scary. Okay. So now for a binary search tree, which is different than a binary tree, because it's a special version of a binary tree. A binary search tree is going to be very, very much along the lines of a binary search and how it's structured. They're not the same thing. They're exceptionally related and interconnected, but they're not the same thing, though. And the general idea of a binary search tree is whenever you're at any node and you look at its data, all of the data in its left subtree must be less than it. And all of the data in the right subtree must be greater than or equal to if you allow duplicates. And the side that you allow duplicates on doesn't really matter. But that's the idea. The binary search tree has very specific properties that we really like. We have more constrained rules on how you're allowed to use it. When you add something to a binary search tree, it must go where it belongs. But because of that, we get nice features like it's easier to search and so on. So yeah, a binary search tree is a binary tree where all values in the left subtree are less than the value in the root node, and all values in the right subtree are greater than or equal to the value in the root node. So yeah, like I said a moment ago, we could have said the values in the left subtree are less than or equal, or the values in the right subtree are greater than or equal. It doesn't really matter which side as long as you're consistent. You just have to pick a side and go with it. For our purposes, the right subtree will be greater than or equal to. And this is assuming we allow duplicates. You could have an implementation where you don't allow duplicates, meaning like you can't add the number 7 to a binary search tree twice. If you say why, because you are inventing it and you can make it however you want. So that's the idea of the binary search tree. But an important thing to note is this must be true for all subtrees in the tree. Okay? What I mean is, like watch, if I have a 10 here, and over here I have a 5, and over here I have an 11, and over here I've got a 19. This is not a binary search tree. Because 11 is bigger than 10. And if this number is bigger than 10, it must be to its right. In fact, let's say I'm adding, let's do a quick test to see, we haven't really even discussed it yet. We haven't gone into the details here. But if I want to add the number 11, where does it go? There's one answer.
19 left.
The left of 19. Why? Well, 11's bigger than 10, so it must be over here. But 11's less than 19, so it must be to the left of it. And there's nowhere else to go, so it must go there. How about the number 17? Where does that go?
Left of the right of the light.
To the right of 11. Exactly. Bigger than 10, less than 19, bigger than 11, must go here. I'm obviously, I'm running out of room, but yeah.
What how the structure of the tree would depend on the order of the nodes you actually put it into. So depending on the order, it can be pretty crappy.
Pretty shitty, yeah. For example, for the fun of it, and this actually jumps ahead a bit in the lecture, but for the sake of, your observation, let's take a moment and discuss this. Let's say I add the number 5. There's an empty tree. Where does it go? The root. Right? Now I add the number 10. Where does it go? Oh, it goes here. Now I add the number 11. Where does it go? Now I add the number 15. Where does it go? This doesn't look like a tree, does it? How about I add the number 20? Where does it go? Yeah, if these things get added in a less than ideal way, this really doesn't look like a binary tree, does it? I mean, it is, because they all have left subtree. They're all just null. They just all don't exist. But notice that, let's do this again. I'm going to add these same 1, 2, 3, 4, 5 numbers. Let's add these numbers again, but just in a different order. Let's add the number 11. Where does it go? The root. Let's add the number 20. Where does it go? Let's add the number 15. Where does it go? Now 5, where does it go? And then 10 would go here. I mean, it's a small example, but this looks a hell of a lot more like a tree than that one did. So the order that you add these elements does matter. But notice that given some tree structure, given some tree, whether it's that one or that one, so given the state of the current tree and a new node, there's one answer on where it can go. If I add the number 21, where does it go? It goes there. There's no other place to put it. If I had the number 21, where does it go? There. There's no other place to put it. Other thoughts, observations, comments? Yeah.
Is it only like integers? Like what if you want to put other data?
Yep, as long as the data.
You just choose how to determine what's greater.
So what, based on what we've seen before, because you asked the question, I'm putting you in the hot seat now.
Yeah.
Based on what we've seen before, what must be the case about the data of type T for us to be able to add it to a binary search tree? It must be comparable. It must have some ordering. But just like the sorted bag, where the sorted bag didn't define the ordering, the data, the type T that we were putting in the bag is what defined the ordering. Integers have an ordering. The bag doesn't dictate the ordering of the integers. The integers themselves dictate the ordering. So whatever the data we want to put in the binary search tree, it must be orderable, sortable in some way. Yeah. So good observation, good question. Other thoughts, questions, comments? Yeah?
Could you add like a third path to one?
Like a third child?
Yeah.
One could do that, but then it wouldn't be a binary tree anymore. It would be a trinary tree, I guess. I guess. Tertiary tree? I don't know, whatever. a threery tree, that's another way we'd call it. So you could, but then it wouldn't be a binary tree. In the same way, like, you could access elements in the middle of the queue, but then it's not a queue. So, I mean, technically you couldn't, because if you did, it wouldn't be a queue. Other questions? I like questions like this. Ask, please. It's boring to just talk at you. All right. Yes? You just, nice. All right, so, yeah. Here's two binary trees. Which one's a binary search tree? Well, the one on the left is. The one on the right is not, because 16, right? Sure, 16 is bigger than 10, and it's bigger than 11, but it's not less than 15. So this right here, it's a sneaky little 16, makes it not a binary search tree. The important thing here is the thing that makes it a binary search tree is all of the elements in the left subtree must be less than, and all the elements in the right subtree must be greater than or equal to. That must be true for all, it's a recursive definition, so that must be true for all subtrees all the way down. So that's what this is highlighting. So here's an arbitrary binary tree. One thing you'll notice is in any binary tree, in any binary search tree, the leftmost node, meaning you start at the top and you go all the way to the left and you can't go anymore. The leftmost node, what is the leftmost node in this example? 3. And 3 is also going to be the smallest number in this binary search tree. What is the rightmost node? 15. If you're like, is it really? Yes, it is. Because 12 is to the left of 15 in this example, right? See? So 15 is the rightmost node, which is also always going to be the largest element in the binary search tree. Why? Because if you get to the rightmost node, if it's a binary search tree and you're at the rightmost node, and you were to say to me, no, there is a bigger thing in there, I would say that's not possible. Because if there was something bigger than 15, it must be to the right of it. If it's not, then it ain't a binary search tree. Same thing goes for the smallest. If you were to say, no, there's a smaller element in here than 3, you can't, I could say that's not possible, because if there was a number less than 3, like a 1, it must be to the left of the 3. It must be in 3's left subchild. But 3 doesn't have a subchild, a subtree. Therefore, it must be the smallest. Questions about that? Are you not convinced? Concerns about it? Whoops. So a binary search tree is a binary tree. So all binary search trees are binary trees, but not all binary trees are binary search trees. So yeah, a binary search tree is a specific case of a binary tree. Therefore, we will have all of the operations that we could do with a binary tree, but some of them will be specialized. And we are going to have a few additional operators. So like a specialized operator will be the add, but like we saw in the examples that we drew out, the adds have to work a certain way. A remove, we can remove something, but it needs to work a certain way. Like, if I said, over here, we're going to ruin the fact that this was a bad one. If I want to add the number 13, where does it go, right? Right? Yeah, I don't know what I was doing there. Let's say we're adding the number 10.5. There. Right? Now if I want to remove the number 10.5, well that's easy, you just remove it. Right? What happens if I wanted to add the number 7? Okay, so I've got the number 7 here. Now what happens if I remove the number 10?
Put 7 onto the 5, then put
I don't know. Adding was a little easier in terms of, well, what do? You just put it where it goes. Remove it, okay, you remove it, but what do you do when that creates like a gap? I don't know. We'll talk about it. And then we'll have like a remove max and a remove min. What's neat about a binary search tree is it's a handy way to make like a sorted bag, actually. But we'll see that, an example of that a little later. Spoiler. Questions? I'm deliberately trying not to go too fast through this because I want to make sure everyone's happy as we go. So everyone's happy? Because this is like the last big core concept of the semester for us, is binary search trees. So I want to make sure you got it. So searching through a binary search tree. Well, because of this special property, think of the search that we did on the general binary tree. Does the node exist? Yes or no? Does it contain the data I'm looking for? Yes or no? So if it exists, but it doesn't contain the data, I got to search over here and search over here. But this is a binary search tree now. It's a little easier for me. Because if I'm the number 10 and I'm looking for the number 7, so I exist, but 10 isn't equal to 7, I need to look through the left and right subtrees. But I don't need to look through both of them, do I? Because if 7 exists, it must be in my left subtree, because 7 is less than 10. Right? So now, the search is way better, because with the other contains, there was a potential for it to call 2 more recursive methods. Look to your left and look to your right if you need to. Here, because of binary search tree, we never need to look at both. You're either going to look at your left or look at the right, but never both, which is better. But we'll analyze this in more detail shortly. So the naive search is this one, right? Does the node exist? Does it contain the data I care about? Look to the left or look to the right. But now I can have an improved version. Because the data is comparable, I'm going to do that compare to thing that returns a negative number, 0, or a positive number. So the node exists, and I get the comparison. If the comparison's result is 0, well, I found it. If the comparison is greater than 0, that means it must be in the left subtree. So do the search only on the left subtree. Or alternatively, do it on the right subtree. But here, unlike before, where it could call both, contains on the left or right subtree, in this example, the binary search, we only ever need to look at one. It'll never call both. It'll only ever call one. So because of that property of how the binary search tree's data is structured, we can now search this better. And it's called binary search for a reason, because it's a binary search. And we know what's the computational complexity of a binary search. Come on, you remember. Log base 2 event, right? You don't need to look at all n things. You only need to look at half of half of half of half of half of half of half. Because remember, every time, assume I'm just some generally pretty full tree. I'm either going to look at this half or this half, but every time I make a decision, I throw away half of the elements. I only need to keep looking at the one half of the two every time I look at something. So that's the logarithmic thing. But if you've been paying attention, like the observation you pointed out, if I have a tree that looks something like this, and I'm looking for the number like 20, the binary tree ain't going to work too well. Because no matter what, it's always going to go, but more on this later. Whoop. Any questions? All right, let's see, where were we? We'll pick up here on Friday.